You know, if you've ever worked with big data sets on the front end, you have probably hit this wall. You're trying to show thousands of records, but all your user gets is a blank screen and that dreaded spinning loader. Well, today, we're going to crack open one of the most common and, frankly, frustrating reasons that happens. All right, let's set the scene. I want you to meet Timothy. He's a junior developer, and right now, he is just staring at a console that's absolutely flooded with a waterfall of angry red error messages. He's pretty sure he's doing everything right, but the computer? Oh, it begs to differ. And this is the error. I'm willing to bet a lot of you have seen this exact message before. Syntax error, unexpected end of JSON input. It's a classic, and it almost always points to some kind of problem with how you're getting or handling your data. Timothy, while he's about to learn that lesson the hard way. So, Timothy's goal is actually pretty great. He wants to progressively render 100,000 user records. He's trying to be smart about it, using the superfast Streams API to avoid hogging memory and to get rid of that blank screen. He wants to show data as soon as it arrives. So, where did it all go wrong?
In this right here, this is the heart of the problem. As data streams over the network, it gets chopped up into these things called packets. So packet 1 might have the first half of a JSON object, and packet 2 has the rest. When Timothy's code gets that first packet, it tries to parse what it thinks is a whole object. But it's not. It's just a fragment, and the JavaScript engine completely panics.
This is when Margaret, a senior engineer, wanders over. She sees Timothy's pain, takes a calm sip of her morning coffee, and immediately zeroes in on the real issue. It's not just a bug. It's a fundamental problem with the whole approach. And she asks this one simple but really profound question. Why are you trying to parse a fragment, Timothy? See, that's the core issue. The stream is designed to deliver data in pieces, but Timothy's code is expecting a perfect, complete object every single time. And here's the challenge, right? When you're streaming a standard JSON array, one giant list inside those square brackets, how on earth does your code know when it's received one complete object? The boundary could be a comma, it could be a closing curly brace, but which one? In a continuous stream of text, it's incredibly hard to tell for sure. As Timothy starts to realize, trying to find that boundary in real time is a total parsing nightmare. You'd have to build a mini parser that's counting every single opening and closing bracket and brace as the data is flying in just to guess where one object ends. It's wildly inefficient and just way too complicated. But then, we get to the turning point. Margaret walks over to a whiteboard, and she's ready to show him a solution that's so much more elegant. One that doesn't fight against how streams work, but actually embraces it. This is the aha moment. She uncaps a marker and writes just 6 letters on the board. NDJSON. See, the solution isn't some clever JavaScript trick. It's about choosing a completely different data format, one that was literally designed for streaming.
So, what is NDJSON? It stands for New Line Delimited JSON, and the idea is just beautifully simple. Instead of one giant massive JSON array, it's a format where every single JSON object is a complete, valid thing all on its own, separated by nothing more than a new line character.
This comparison just says it all. On the left, you've got standard JSON, this huge monolithic array. You have to wait for that very last closing bracket before you can parse anything. But look on the right with NDJSON. Each object is complete and self-contained. The boundary isn't some tricky syntax, it's just a simple, reliable new line.
Okay, so the format is brilliant, but how do you actually process it in your code without hitting that same packet slicing problem? Well, this brings us to a really powerful yet simple technique called the accumulator pattern.
And Timothy asks the exact question that we're all thinking. How does that fix the packet slicing? I mean, the network is still going to send fragmented chunks of data, right? And here is the genius of it. A new line character, that simple \n, is a universal and, most importantly, a completely unambiguous boundary. There's no guesswork. When your code sees a new line, it knows with 100% certainty that everything before it is a complete message. So here's how the pattern works. It's pretty straightforward. First, you create a little temporary string, a buffer, to just hold the data as it comes in. As each chunk arrives, you just add it to the buffer. Then you scan that buffer for a new line character. The second you find one, you slice off everything before it. That slice, that's a guaranteed complete JSON string that you can safely parse. Then you just repeat the process with whatever's left in the buffer. So Timothy refactors his code to use this new accumulator pattern. He hits refresh, and the result?
Well, it's exactly what he was trying to do from the very beginning.
The change is just immediate. That loading spinner? Gone, instantly. The data grid starts populating row by row perfectly, as each object gets parsed from the stream. There are no memory bottlenecks, no blank screens, and best of all, zero syntax errors. It just works.
The real key takeaway here is this. The problem wasn't the stream, and it wasn't Timothy's goal. The problem was this fundamental mismatch between his data format and what he was trying to do. By choosing a format that actually respects the boundaries of streaming data, he was finally able to achieve that true progressive rendering he wanted.
And that really leaves us with a final thought to take back to our own projects. Your choice of data format, it's not just some minor detail. It is a critical part of your system's architecture. So the question we should all be asking is, are we always choosing the right one for the job?